All right, welcome to today's Explainer. We're diving into something absolutely wild today. The ultimate invisible currency of the universe. I'm talking about energy. It's kind of like the ultimate backstage manager, right? Constantly working behind the scenes, constantly shifting forms, and acting as the fundamental driver that makes literally everything in our physical world happen.
So, let's start with a little riddle. What do a drawn bow, a book falling off a shelf, and a microscopic living cell actually have in common? On the surface, no way they're related, right? Well, the crazy truth is that every single one of them plays by the exact same hidden physical rules. They are all actively demonstrating the transfer and storage of energy.
Okay, let's dive into this. In the physics world, energy is basically just the baseline ability to cause change. It's measured in joules. But how does this invisible currency actually move around? Well, it happens through work. Doing work on an object is literally just the physical mechanism of transferring energy to it. You do work, you change the object's energy. Simple as that.
Now, energy is a master of disguise, but let's introduce its first big persona, kinetic energy, or KE. This is the energy an object has purely because it's moving. Think of it as the energy of the now. Every single moving object you see, whether it's you out for a run or a planet orbiting the sun, has kinetic energy. But exactly how much it has depends on two very specific things.
So the formula for this, 1/2 mass times velocity squared, actually hides a pretty major mathematical secret. Pay special attention to that v, the speed. Notice how it's squared? That tiny little detail has massive, massive real-world implications.
And this brilliantly illustrates why highway speed limits are such a big deal for public safety. Because of that squared speed rule we just talked about, doubling your speed doesn't just double your kinetic energy. Actually, scratch that, it quadruples it. 2 squared is 4. So mathematically speaking, a car traveling at 100 kilometers an hour doesn't have twice the energy. It carries exactly 4 times the destructive kinetic energy of a car traveling at 50 kilometers per hour.
Let's put some real numbers to this, say with a pitched baseball. Take a standard 0.145 kilogram baseball, and let's throw it at a really fast 40 meters per second. When we plug those numbers into our formula, we square that 40 meter per second speed first, which gives us a huge multiplier.
Run the rest of the math together and boom! Here is our punchy conclusion. 116 joules. Just because it's moving at 40 meters per second, that tiny, lightweight baseball is packing a massive 116 joules of kinetic energy right into the catcher's mitt.
All right, let's switch gears and check out the second disguise of our shapeshifter, potential energy. If kinetic energy is all about active motion, potential energy is stored energy. It's safely tucked away, waiting to be unleashed, strictly because of where the object is, its condition, or its physical shape. It's essentially just sitting there waiting to convert right back into kinetic energy.
The one you interact with literally every day is gravitational potential energy. When you lift something up against gravity, you're actively storing energy in it. And the amount depends on its mass, the constant pull of gravity, that's our g, and its height.
Now, here is a super fascinating quirk about that height variable, h. Where you decide height equals 0 is completely arbitrary. You could pick the floor of your room, the ground outside, or even sea level. It doesn't matter. The math still works perfectly because what we really care about in these physics equations is the change in height between two different spots.
Let's run another scenario. Imagine doing the work of lifting a 2-kilogram book onto a shelf that's 1.5 meters above the floor. All you do is multiply that mass, times the gravity constant, times the height.
And what do you get? Exactly 29.4 joules. By doing that upward work against gravity, you've successfully stored 29.4 joules of potential energy in that book. And because energy is the ultimate survivor, it just changes shape. If that book accidentally gets knocked off the shelf, that exact 29.4 joules of potential energy converts flawlessly back into 29.4 joules of kinetic energy right before it smacks the floor.
But hey, position isn't just about gravity. Deforming material stores energy too, and we call this elastic potential energy. You can pack this energy into a squished spring, a stretched rubber band, or, like we talked about in the very first riddle of this explainer, a drawn bow. The more you compress or stretch the material, the more elastic energy is stored inside.
Now, what's really interesting here is how these exact same rules of physics jump straight over into biology. Check out this concept. Chemical energy is a form of potential energy. It is stored in the bonds between atoms. We aren't just talking about metal springs and baseballs anymore, folks. We're talking about the literal building blocks of life.
Right inside living cells, these principles are happening constantly.
During photosynthesis, light energy gets converted into stored chemical energy in the form of glucose. Then, through cellular respiration, that energy is released to make ATP. Breaking or forming those atomic bonds is just another incredible, beautiful way of absorbing or releasing potential energy.
So, we've got the core concepts of kinetic and potential energy down. Now, let's put you to the test. I want you to pause and think about this classic gravity puzzle. Which object hits the ground with more kinetic energy? A 1 kilogram ball or a 5 kilogram brick, if they are both dropped off the exact same height? Lock in your guess.
All right, let's reveal the answer. Think back to those formulas. The 5 kilogram brick has more mass, right? So it starts out with way more gravitational potential energy. Since all of that converts to kinetic energy on the way down, the heavier brick absolutely smashes the ground with much more kinetic energy. But here is the really wild part. Despite that massive difference in impact energy, they fall at the exact same speed.
So, the crucial point is, how on Earth can a heavier object hit with more energy but not fall any faster? It all comes back to Newton's second law. The acceleration is identical for both, rg, 9.8 meters per second squared. Why? Because yes, gravity pulls way harder on the massive brick, but that extra pull is perfectly canceled out by the brick's greater inertia. It resists moving more, which exactly compensates for the stronger pull, making them hit the ground at the exact same time.
We've seen how energy is basically this immortal shapeshifter. It transfers, it converts, but it never ever disappears. From stored potential, to rapid kinetic motion, to atomic bonds in a cell, or a baseball flying through the air. Which brings us to one final provocative thought for your next daily commute. If the math of the universe says energy only ever transfers and converts, where exactly does your car's massive kinetic energy go when you finally hit the brakes to stop? Think about that.